Thank you. I appreciate it. Cool. Hello. My name is Jack Lindamood, and my talk is about genetic algorithm discovery of worst-case Go sort inputs powered by AWS Batch. This is what happens when an SEO company writes your title slide. So kind of worked out pretty well. I don't have necessarily enough time to do a full introduction of ML and AWS and Go, right? So I'm going to give you ideally like the inspirational parts of it and the important parts and kind of how I got to this title slide. So I started here. I was looking at the documentation for sort, and it says big O n log n, right? But it doesn't tell you how it's implemented. And maybe future versions of Go implement it differently. And then I kind of thought deeper into that, and I was like, all right, here's the real question. If you have a black box API, and you wanted to discover the worst inputs for that black box API, what would you do, right? So that was like the basis of my thought. This might be a sort function. It might be an API call on a remote server, and you have like a stopwatch, and you want to make the server crash. It could just be this general category of, I don't want to look into the code, I don't want to look into the API, but I want to make it perform very poorly. And since I like Jurassic Park, I was like, hey, let's just use genetic algorithms. So I want to introduce genetic algorithms to you in a lighthearted way. So I'm going to invent a scenario and kind of go through a genetic algorithm for it. So in this scenario, you're a movie producer, you want a really good plot for a movie, and you can kind of focus group the plots, right? So we start with a plot idea, like a wizard joins an NFL team. This would be called a chromosome in your genetic algorithm. And it's basically one way to solve the problem. So now I want lots of different ways to solve this problem. So I think, OK, maybe The Rock founds a tech company, or it's like Pixar, but they're all sunglasses. This is actually a fun game. Let me see if I can play this with tech startups. It'd be like Uber for phones, or Twitch for banking, or Apple makes bottled water. Oh, that would be so expensive. OK. So this is like the idea, right? Like you kind of create ideas for your movie plot. Now you need a fitness function. So the fitness function for your genetic algorithm is just going to be basically how bad or good it performs. Ideally, it's how good it performs. But if you're trying to make an API slow, the fitness function would be how bad it performs. So you focus group your movie plots, and you're like, oh, this one got 5 stars, this one got 0 stars. And now you need to make new solutions for your genetic algorithm. So you take 2 movie plots, and you kind of combine them together somehow. And here I would take, all right, a wizard joins an NFL team. The Rock founds a tech company. Maybe wizards found a tech company. This is called crossover. You can do this many different ways. And you don't even have to use 2 parents. You can use 3, 4, 5, 6 different parent solutions and kind of combine them all together. The final part of genetic algorithms is something called mutation. And that's where you don't want to do mutation too often, just like in natural selection. But you kind of sometimes want to mutate things. It helps you get out of local minima or local maxima. So in this case, for example, maybe wizards don't found a tech company. Maybe dogs found a tech company. Interesting fact about this dog-founded tech company, they're named Pack, and they get $1 billion from SoftBank. Yeah, pretty interesting. So we have a new population here, which is basically these mutated and combined solutions. Now we have too big of a population, so we need to do something called survivor selection and kill off. Ideally, you keep the fittest solutions, but you kind of kill them off in a somewhat random manner. And you keep doing this, combining solutions, mutating them, combining them, mutating them, until finally you get the ultimate solution for a movie, which is really something that cannot be evolved further. I think the only way I can review this movie is to call it breathtaking. Absolutely breathtaking. I don't think you can do better. All right. So that's like the introduction, the fun introduction to how genetic algorithms work. Let's kind of apply this to sorting and Go and kind of see what happens. This is the basic algorithm for sorting in Go. So you want to sort quickly, and quicksort is a great way to sort quickly. There are actually anti-quicksort timing algorithms that you can use to generate really bad quicksorts, and Go actually uses them in their testing. But the problem with quicksort is it works really fast, but it doesn't always work in login, right? So Go does this kind of three-part step. They say, OK, if it's a really small set, don't even bother with quicksort. The constant time is going to be too much. Just go ahead and shell sort it. If you've quicksorted and quicksorted and quicksorted, and you're in one of those like really bad cases, you still want to guarantee in login time, right? So then you fall back to heap sort, and you say, all right, if quicksort's not doing its job, let's just heap sort everywhere. Otherwise, you just kind of keep pivoting. This is actually, I think, like an interesting class of problems where you kind of guarantee a good worst case algorithm while also trying to have an optimal general case algorithm by falling back to something that can guarantee the runtime you need. So I think it's pretty interesting. All right, so what is a chromosome for sorting? So a chromosome for sorting would be like the array that you want to sort, OK? It's not so hard. What would be the fitness for this algorithm? So it would basically be how bad is it, right? So for this algorithm, for this array, the fitness is 12 for Go. That means it takes 12 swaps to create this chromosome, to process it, sort it. Crossover, you can do crossover many different ways. One way to do crossover, if you think of like actual human genes combining, you take sections of each. One way to do it with sorting would be to just kind of split the array in half and take each half. But the general intuition I'm applying here is that if a section of one thing sorts poorly and a section of another thing sorts poorly, maybe if I kind of combine those two ideas, they also sort poorly. And then finally, mutation. Again, lots of different ways to do mutation. You could like swap different indexes. Here, I just kind of randomly change one. All right, so we have all the base components for genetic algorithms and sorting, right? So we have how to define the fitness function, the crossover functions, the mutation functions. Let's actually architect from scratch a genetic algorithm in Go. The first problem you're going to run into is, all right, what files go where? This is kind of called package layout or code layout. There are a lot of different philosophies on how to do this. I personally prefer flatter, shallower hierarchies. An alternative way to do this might be to put mutation and crossover in their own packages, but then those packages would be pretty small. Why bother doing that? Just kind of scoop it together. And genotype is a way to describe what I'm actually genetic sorting. Now, we all use Go for the parallelism, right? No, not really. I use it for a lot of other reasons as well. But there are certain aspects of machine learning algorithms that make them very parallelizable. This is the classical way to kind of use parallelism in Go. So I have this huge array of a population, and I want to kind of calculate the fitness for all this population, so that would be applying it to the API black box. In our case, it would be sorting it. So I spin up some number of Go routines. I associate them with a mutex, feed the Go routine, feed the individuals of the population into a channel, process the channel, and then kind of wait for them all to finish. This is like the general way that parallelism is done in Go. Now, there was another aspect of this that kind of turned out interesting for me. So let's think that we're in the phase where we want to create a new population. To create this new population, we need to create 100 new chromosomes. So one way to do this would be like I have up here. You have a main Go routine that feeds 100 creation methods to a channel, and then worker Go routines that read the need for creation from that channel, create a chromosome, put it back on a channel that's then read from a main Go routine to get your 100 DNAs that you want. The problem here is that you have two mutex-style bottlenecks here, right? One of them is feeding all of the commands to make new chromosomes, and the other is reading from the buffer of created chromosomes. Another way to solve this is to pre-create the space for the created chromosomes. So for this method, let's say I wanted to make 100 chromosomes, right? I could create an array of 100 empty spaces, and rather than feed commands to make things, I feed indexes into this worker channel. So now all my worker go routines, they read a number, like 3, 4, 0, and that number says, I'm going to create a child, and I'm going to put it in index 3, or I'm going to create a child and put it in index 4. The advantage of this is that I don't need locking or coordination when I finish creating the new chromosome. I can just put it directly in the result. An alternative to do this would be to pass a pointer rather than an index. But in this case, the index kind of is a pointer. And this is a pseudocode for how that was created. So it looks very similar to what I had previously. I have ret, which is how I name all my return values. Ret is a new population, and I feed into an index channel numbers from 1 to some value. And then I just read off that, create new individuals, and put them directly into the returned value. The next thing you're going to run into is randomness. Machine learning algorithms are often very random number generation heavy. And if you use randomness in the Go standard library, this is code copied from the Go standard library. So rand.int31 is going to use this instance called global rand. Global rand uses a source called locked source. And locked source calls a function lock. The problem with this is that if you have many different Go routines all trying to do machine learning at the same time, they're going to lock on this global mutex. So my solution for this is to pass the random number generation as a parameter in my call stack. You could have thought of a different way to do this might be thread local state, not in Go, but you don't need it. You can just put randomness as part of the parameter to mutation and pass it directly down the stack. So here I have a new random for every different Go routine that I'm going to run in my process. All right, now the final part of this, deploying and running it using AWS Batch and ECS. So the first thing you need to do is you have this Go code. You want to run it in AWS. How do you run Go code in AWS? There are 2 real ways and 1 bad way to do that. The real ways are you use Lambda or you use Docker. And the really bad way is you try to spin up an instance and not use Docker. Don't do that. Gives me very scary thoughts of managing dependencies and Puppet configs and cron jobs, and it's like very difficult to kind of maintain. So I recommend Docker. There's kind of a problem with that. It's not obvious how to make a static binary in Go. And it's a bit of a black art, and there's lots of posts out there. If you type into a search engine, Docker Go, you're going to see a bunch of blog posts about people, oh, you do all these steps. So there's a ticket out there that says a proposal, we should add a static flag to the Go build. This proposal has 200 emojis. And since proposals are accepted proportional to the emojis they get, I predict that this will be soon added to Go. There is traction on this proposal. So don't furiously write these numbers down. I would have used QR codes if I was more insightful. But the slides will be public. These are recommended homework for trying to use Go and Docker together. They're resources that I've kind of found pretty useful. All right, so now we have this Docker container. It's got some Go code. Cool. Now we need to actually run it in AWS. There are 5 main components to running your batch code in AWS. And there's like no way I have enough time to go into enough detail for all of these, but I'll try to give you like a general overview and a general sense of what they do. So the VPC is like your networking glue. ECR is the like Docker hub. It's the place you put your Docker container. EC2, that's the actual machine, the virtualized machine that's running your code. DynamoDB is a place to store the results for it. And then batch is the thing that's kind of orchestrating all of that. I personally use Dynamo for data if I'm kind of like lazy and I don't want to spin up anything and I don't want to spend a bunch of money and I have like maybe 5 things I need to store. Dynamo is like a great place to kind of just put it and forget it. VPC is super abstracted and not overly complicated, but very complicated because it's solving a complicated problem. These are the resources that I've found very useful if you want to learn more about VPC. And you don't have to write these down. The slides will be public, and you can click on them later. But let's see if I can give you an explain like I'm 5 for networking in AWS. So these are the components that you're going to make. The first one's your VPC, so that's your network. Your network is going to be divided into availability zones inside your region. Those will be your subnets. The network itself might need to connect to the real internet, right? Because your internet isn't the real internet. So I visualize this thing, the internet gateway, and the gateway attachment is that closet in Narnia. You know how you're like in the house, and then you go through the closet, and you're actually in Narnia. So Narnia is the internet. You kind of need to go through this thing to get there. So that's the internet gateway. And then there's a bunch of things around routing tables and routes and table associations and security groups that kind of configure how network traffic is routed. You want to send public traffic through to Narnia. You want to send private traffic through to your own VPC. These are not, when I initially learned this, I did a lot of copy pasting, I'll be honest. And I wouldn't feel shy from doing that yourself. But after you copy paste it, try to delete things from that copy paste and see why they do or don't work. And I think that was like the best way for me to kind of learn these things. The next thing you're going to have to understand if you run anything in AWS is that you don't actually get real computing power. You get this virtualized thing. So like, yo dog, I really heard you like virtualization. So we have a Docker container, and we have virtual CPUs, and we've got like VMs, and we've got all these things. So you're like very separated from the actual computer that's running anything. In AWS, especially with batch, you might ask for 16 virtual CPUs. That doesn't mean you get one C4-2x large instance. It doesn't mean you get 2 C4x large instances. But you get generally 16 threads that you can kind of depend on executing independently. Independent-ish, because you might be sharing your resources with someone else. So if your computer is running really slow in AWS, just kind of shut it down, spin up a new one, see what happens. Again, homework to kind of learn more about this. I think, as kind of an aside, I think that AWS does a really good job documenting their APIs, but it's kind of an acquired skill, like reading Shakespeare plays, right? You know, you read Shakespeare, and you're like, OK, this is English, but I don't really understand all these words together, and you read it like 5 or 6 times. I think the AWS docs are kind of like that, where it's English, and you know, it's very well written, I mean, and probably written by many authors. But I wouldn't get too discouraged. So like, don't read it and kind of get discouraged with the detail of it. Just start small, go deep, and experiment. So you need a place to run it. This is EC2. What I have here is some example CloudFormation that spun up this EC2. The important part I want to call out is the minimum CPUs of 0. This is a way of allowing your resource to auto-scale to 0 if you're not using it. If you forget this, you may get a message from someone in billing at your company that says, why are these things spun up? And that may not be so great. But Amazon may like it. The next thing you need to do is you need to pass configuration into your batch jobs. The problem with CloudFormation is that if you make a Dynamo table in CloudFormation, it's going to get a very long name. It's going to get some auto-generated thing with like a number at the end. You don't want to copy-paste that. So you can reference it directly inside your CloudFormation using ref. I don't want you to get too deep into the CloudFormation itself. I think that the general point here is that you can use CloudFormation to pass these environment variables in. Permissions in AWS. There are two types of people that do permissions in AWS. There are the people that use asterisks and the people that run into problems. Those are the only two types of people. And if you try to do permissions in AWS, I'm not saying they did a bad job. Like, it's a very well abstracted solution, but it's very well abstracted. So to kind of break this solutions maze down for you, so you have AWS Batch. It needs to do things. So it has a role, right? It has a service role. But what does AWS Batch need to do? It needs to spin up EC2 instances. It doesn't need to talk to Dynamo, so it just needs permission to the EC2 instances. But what do the instances need? Well, they need a role too. And what does that role need to do? It needs to pull in containers. It needs to maybe start jobs. It doesn't need to talk to Dynamo. So all right, you've got the instance. It starts a task. What does the task need to do? It's the thing that talks to Dynamo, right? So don't try to put your Dynamo partitions at the top. Just, it's a maze. And if you run into problems with this, it's OK. Like, just kind of work through it. I think one way that really helped for me was don't think of AWS Batch as like a magic part of Amazon. Think of it as you had written it yourself. So if you had personally written AWS Batch, what permissions would it need? Now you want to trigger your job. The AWS CLI is a great way to trigger jobs. And it is kind of the power tool, the PowerShell into AWS. Everything that it runs outputs very, very long JSON. And if you want to get any data out of that JSON, you need to use something called JMES path. It's actually built into the CLI for you. This is just an example of some of the syntax of it. So if you have JSON that looks like the top, maybe some locations and states, you can run a command that says, oh, if the state's Washington, get the name, sort it, and join it, and then kind of output that. So these are the fancy computations you can do with it. And that's what I use when I was writing my bash scripting. So I have this CloudFormation stack. It's got a name. I want to go into the stack. I want to get the outputs that match the first variable of my bash function, and then get the output value of that output. So the end result here is that if I call the bash function stack output job queue, I get the actual job queue from the stack. Finally, the last step, you run it. Whew, OK. Don't get too bogged down into the syntax of the run command. The important part here is that you can use the environment variables of your Docker container to pass configuration into it. So here I might configure how large the array is that I'm looking into. So you run it. AWS Batch manages for you, spinning up the tasks, spinning up the containers, auto-scaling your EC2, and then auto-scaling it back down when you're done. And you can look at the logs for your results in CloudWatch logs. That'll just be the aggregated kind of standard output. The sample code for this is on my GitHub, CEP21 genetic sort. And that is it. Thank you.